All right, let's start. It's my great pleasure to welcome Vijay Subramanian to the SNAPP seminar series to talk about towards learning-based approximately optimal control in constraint decentralized dynamic teams. Vijay is a faculty at the University of Michigan. He's been there, if I'm not mistaken, for about 10 years. He got his PhD prior to that, a while prior to that, at UIUC, and has had various visiting positions in the last few years, including back at UIUC. His research interests are in stochastic analysis, random graphs, multi-agent systems, and more generally sort of network-based analyses. And I think some of that he will tell us about today. Vijay, the floor is yours.
Thank you, Daniel, and thank you for the committee for inviting me to give a talk here. So I'm going to talk about some of the work in my group and actually at Michigan on dynamic teams and multi-agent systems in general. So the work I'm going to talk about essentially are going to be on two topics, which is from these two papers, the CDC and the Infocom one, and it's primarily done by my student Numan Khan, who's on the audience from what I see. And towards the end, I'll sort of talk about a little bit about another past student's work, Su Gao, as well as another student who will come up, again, graduated student, Dengwang Tan. Some part of this work is in collaboration with Ujjwal, Subramanian, Dheeraj, and Srinivas Shakotai at Texas A&M. So, so in keeping with another friend of mine who told me the best way to do this, or I've seen him do this, is to go with the, acknowledgements first. So I will start with acknowledging my student, Numan. He's done a lot of this work. I mean, all these excellent students have actually taken this work forward, which has been great to work with them. Shu Gao is the one who graduated. I would also like to acknowledge Srinivas Shakotai and his group. Next will be my student, Dengwang, whom we started on looking at some of these multi-agent systems together and learning about it. And I will talk about his work towards the end, relative to games. There are a few other people I need to acknowledge who've been sort of extremely helpful in helping me learn this topic. One is Aditya Mahajan, who's a faculty at McGill, Montreal. He knows this topic very well, and I've learned a lot from him. And similarly, my senior colleague, Dimos Tenekitsis, he has done seminal work in this area. His name will pop up many times. And finally, I'd like to thank NSF for supporting this research. Anyway, so let me proceed with the topic per se. So I'm going to generally situate this work in decision-making in multi-agent systems and networks. And I'm giving you a few examples on the side, like connected autonomous driving, smart grid, so on and so forth. So this is essentially a group of agents or decision makers who interact with each other in a shared environment. And it comes up in many forms, and it's particularly interesting in today's context to explore this. There are extreme possible configurations of it. There are two extremes, as in one is all agents are cooperative. They work towards a common goal. This is what's called a team problem. And this was initiated back in the day by economists Marshak and Radner. And the other side is the game setup where everyone is sort of competing, and that's have individual goals. And that's, I'm giving you a reference here, but even that was sort of originated roughly in the 60s and 70s. Interestingly, that in that period, they did talk about these systems quite a bit, and there were a lot of conceptual leaps made. They didn't have the computation resources we have today, but what I want to bring about today is essentially saying, yes, with that concept, those conceptual leaps and additional ones that we have been developed over the years, including some from my group and many from Michigan, actually. I think we can address some of these problems with the computational tools we have today. However, multi-agent systems in general with decision-making are challenging. There are several unique challenges. One is this multi-agent interaction. And the way you want to see that more importantly is through complex information structures. There's something called information asymmetry, which I will talk about a lot. Essentially, you do not know what the other agent knows, but you have to infer through actions. And that's a problem. And You may also not know the entire environment, so partial observability is another issue that comes up. What will be sort of an important feature of today's talk would be joint constraints, and we'll see how that complicates things and how we should think about that. As I mentioned, while there are these two extreme configurations, and there's lots of things in between, games of teams and so on and so forth, I'm going to talk about today, focus essentially on the cooperative setting of a team, and towards the end, talk a little bit about what happens with games. Right? And I do want to say one thing here. I'm assuming that the team is already formed, and no one has an incentive to leave the team. This is unlike the cooperative game theoretic setting where you also have to incentivize people to be in that team or cooperate, right? So that's already been taken out, and we just assume that the team will not break. All right, so this talk, I would also situate this broadly within the sequential decision-making framework. And a particular concept that will sort of run straight through this would be a concept called information state. And I think this is important, and I feel like all this is a conceptual concept, and that actually helps a lot in developing algorithms, both in the case when you know the models, the planning setup, as well as when you have to infer it through data-driven decisions and through data. That would be the learning setup. So one of the problems in any sequential decision-making setup is as you take decisions or as the environment evolves, the information increases over time. So you have this history that you're working with. In some cases, it can be private history, especially if you have multiple agents. And this essentially, working with this entire history leads to increase in complexity and memory and a host of such issues. One of the conceptual ways that have been used to sort of handle this issue is something called an information state. It's a sort of a sufficient statistic of history that is relevant for decision making. And so many of the references I give are going to be somewhat seminal references. There have been lots of things after that, but I would say it's good to start with the seminal references in these topics in any case. So just to put it in terms of words, this is a compression of history sufficient for decisions, right? So decisions, optimal decision making, all of that comes under the umbrella when I say that. So what this does, essentially, it simplifies the search for optimal or good control policies and yields algorithms. Essentially, what it does is allows you to sort of summarize the past nicely and predict the future. And essentially, that gives rise to things, what we call sequential decomposition or dynamic programming. And in the learning context, the same thing enables learning-based solutions because you have a sort of a compressed summary, which is smaller than the history, which is much larger. And that leads to algorithms, which is the topic in reinforcement learning. So a few examples here would be important so that the concept gets a little clearer. One of the simplest things is looking at Markov decision processes. And when we teach it, we make a lot of effort to say that you can just look at policies that depend on the current state or Markov policies, right? And that is a compression of the history, and that is an information state that we use quite commonly without thinking about it in that sense. The nice thing here, and this is something that is going to come up many times, this information state is both model and strategy independent. I don't need to know what strategy you used or the model especially. I can just focus on the current state and I'm fine. Okay. And it wouldn't be an exaggeration to say that this is one of the reasons why there's been so much development on reinforcement learning, because these two aspects actually help a lot. So when you go to partially observed systems, which will be a sort of precursor to going to multi-agent systems, we do have an information state. And again, we discussed that a lot in our courses. This is what's called the belief state or the nonlinear filter. And the issue with that, which is not, I mean, there are one thing that everyone discusses, and it's also done a lot in the reinforcement learning literature, is that this is model dependent. But the one thing that is not emphasized as much, but it's buried in there, it's actually strategy independent, and that's critical. And that's why there's a lot of excitement now and actually a lot of work on developing methods, reinforcement learning methods for POMDPs. Nevertheless, this fact of it being model dependent has led to challenges. I think this computationally is a hard problem. I will say that in this context, there is a model and strategy independent information state, but that essentially grows with time. And so it's not as helpful as the one with the MDP, right? So this contrast is something that will be coming up quite a bit in my talk, right? So one of the things that I want to sort of talk about and then go talk about our work is how about information states in multi-agent teams. It's good to understand that before we understand the work that I'm going to talk about. Okay. So before getting there, it's good to focus a little bit more on the challenges for even cooperative multi-agent team problems. As I said, information asymmetry is a big challenge. So each agent is working with their private information and no agent will have a sense of the entire information in the system. So what agents need to do is use complex reasoning, just as in games, to infer private information when acting, right? And what this leads to is what's called signaling. And this intertwines strategies and this makes it quite complex. And these problems also have what's called non-classical information structure. Well, what we know in MDPs and POMDPs is that the agent who's taking the action has all the information from the past. He may not know the state exactly, but all the information that is there is available. Whereas in these multi-agent problems, information asymmetry essentially means that I don't have the full information and I have to still take decisions. This makes dynamic programming type ideas very hard. Sequential decomposition is difficult. And the rescuing concept here is the characterization. If you can characterize an information state, that allows for sequential decomposition. So a lot of the development, conceptual development, is in coming up with an information state. The other thing that is usually an issue here is if you're trying to do any kind of learning or even like algorithmic approaches, if you have concurrent policy adaptation by different agents, you have a non-stationary environment, and that actually complicates learning quite a bit. I will add that teams are much simpler than games. All these complications exist in games, but games you also have to account for people deviating. Whereas teams, you don't have to use that. Deviations don't need to be analyzed, and that's a big saving grace. And I will comment on this towards the end of the talk. Nevertheless, despite all of these, the problem is it's sort of more complex than a POMDP, so it's NXP complete. It's worth looking at it in the context of the Witzenhausen counterexample as well, which is a linear quadratic sort of setup, linear Gaussian quadratic setup where linear policies are not optimal. We have to look for nonlinear policies. Again, that's a way of understanding that the solution complexity increases. The other issue here is that in these problems, even if, so there are a lot of examples in the linear quadratic setting, Gaussian setting, whereas if you go to the standard discrete setting, the Markov decision process, there are very few examples that are solved. So there are few benchmarks. I will put in a plug for my student, Dengwang Tang. With his postdoc advisor, he's got some work where you actually can come up with an algorithm to solve for it using the points-based method that is used for POMDPs. And using his tool, you can solve for many more examples. Okay. So moving on further, solutions do exist for these cooperative multi-agent problems. And these are actually conceptual. And one of the first approaches was this thing called the person-by-person approach, where you think of each agent taking a best response to the action of the other agents. And it turns out in the team problem, the social welfare maximizing the team optimal problem is also a Nash equilibrium. And so the person-by-person optimal will be searching for a Nash equilibrium. And if there's enough structure in the problem, things like convexity and things, you do get to that socially optimal solution. Nevertheless, it's not guaranteed to give you the socially optimal solution. There's a lot of research here in the linear Gaussian setting. The other approach is a designer's approach, is for a designer who knows the entire the model, so all the and then prescribes actions to all designs actions for the policies for all the agents. This gives you a solution, but it's very complex. And it's more, I would say, to understand the problem than necessarily to develop a solution. A more interesting, a more recent approach, rather, by Nair, Mahajan, and Teneketsis, which was developed here at Michigan, is the common information approach. And I believe that that approach is a good path to developing solutions for these problems. Right? So I'll briefly describe the common information approach because I will need to mention it much later on. So what it does is it transforms the problem, the multi-agent team problem, cooperate to a fictitious coordinators partially observed Markov decision process using common information. And once you're in the Markov decision process set up, then you know how to solve it. This coordinator does lots of details I'm suppressing because this is not the focus of this talk, and plus it's their work. The coordinator uses the common information to provide prescriptions to each agent. Right. And these prescriptions are essentially partial functions or truth tables, essentially saying, if your private history is X, you're going to take this action. So you just list out the entire thing. And these prescriptions become actions of the coordinator. And viewed in this manner, you get a partially observed Markov decision process. And the equivalence to team problem holds when these are prescription chosen deterministically. And then you can sort of show that each agent can instantiate the coordinator, and that solves the problem. Okay, this is a very high level that I'm giving this description. And what this provides is this approach gives you an information state. Again, I would like to insist that this is model dependent, but interestingly, it is strategy independent. And that's why I believe that this approach can be used to develop solutions. So having given all this backdrop, I'm going to then use this to start talking about our work. I will start initially with something that is more in the stochastic control or the planning setup. This is going to be looking at a constrained, decentralized, partially observed Markov decision process. And because they have constraints, we'll have to see how you can think of even solving it. And I'll present some results on that and then show you how that's applicable in one particular example, and also say what other utilities that we have seen of it. And then I will sort of say how I can use that to develop structural results and show some idea of how learning can apply there. And thereafter, talk about games and then conclude. All right, so let's start with the first thing. This is the multi-agent constrained decentralized POMDP. I know it's a mouthful. Nevertheless, let me tell you what the process is. So you're going to have n cooperative agents. The agents are fixed. They are there all throughout. They're taking action sequentially, and I'm going to look at a discrete time setting. There's some environment with some internal state ST that lives in some state space S. This will be some general topological space. I will mention that a little bit later. So after all the agents have formed a joint action, so I'm going to collect the action together as a vector, it will be AT. I'll tell you more about the space of actions. And this, they have to use their own information to construct these actions. The state of the environment will evolve to ST plus 1. After the state evolves, all the agents will receive observations. Now, the observation I'm going to spell out is this vector OT plus 1, and it has the superscript is 0 to n, and I'll specify what that is very soon. But there is n plus 1 dimensional observations in some sense, and there are n agents. Okay. The team incurs immediate costs. When we go to the learning context, we have to insist that the values are in a countable space as well. But nevertheless, in the planning context, it can be more general. It's an immediate objective cost for the primary objective, denoted by C, S, T, A, T. So it depends on all the actions and the unknown environment, possibly unknown environment. And you have an immediate constraint cost, D, S, T, A, T again. This is k-dimensional. And these are potentially joint constraints or could be individual constraints as well. The example that I'll illustrate later on will tell you how you can think of a joint constraint in this context. And the joint constraint need not involve all agents as well. Right? So as I said, the observation has n plus 1 dimension. And the way you want to think of it, if it has superscript 0, it's a common observation observed by all agents. And if it has superscript n, it's observed by agent n only. Okay. So we are distinguishing the observations as one component that is observed by everybody, and a subcomponent that's observed by a component that's observed by a particular agent. So pictorially, you have this figure down here. So you have the state, essentially, state evolves by this machine. However, the environment evolves after all agents take actions. And once it evolves, the observations are provided to the agents, and the costs are generated as well. Right? So it's in this context of a problem that I want to study optimal decision making. Okay. So as I said, the decision process is a general topological space. However, my observations are going to live in countable spaces, right? So I look at my observation space as script O, which is going from, which has common observations and per agent observations, right? We allow, in this context, our action spaces are going to be finite. I think we know how to be there. Maybe this could be generalized, but for now, this is sufficient. This is complex enough. Again, the actions are assumed to be, spaces are supposed to be factorized, as in each agent has its own action space. In this context, we also have a general transition law. So given the current state, environment state, and the joint action, both the state and the observations evolve. And this is given by, this is essentially a Markov decision type process type transition kernel. And since I have a general topological space, the next state lives in some Borel measurable set. I mean, this is the probability given that it lives in it takes values in set B in S, and the observation is O. Right? To specify this properly, you also need an initial distribution, and we have an initial distribution on the state and observation, and that lives in. I mean, we use the topology of weak convergence for all the probability measures on that space, and we pick one of them from that as the initial distribution. So having said this, so let's see what is the optimization problem. I need to first specify how actions are going to be taken. So you have this common history, which is at time t, you have all the common observations seen up to now. So it's O 1 to t, but superscript 0. Each agent also has this private history, which is the private observations, and anything you can subtract the common observations from there. And so that it is constructed, each agent also knows the action that they have taken. So you look at the previous private history plus the new actions plus the the private observations minus anything that is common. This is the private history for that agent, right? And so the policy of each agent has to depend on the current history that it knows it. Right? So I'm going to denote the policy of each agent by U superscript n. And it's of the form U 1 to infinity, well, 1 all the way to not including infinity. So for any finite time, it's specified at time t by some function, which is going to be taking as input the history, the common history, as well as the private history. And since we are in a constraint setting, we will assume that these actions actually are randomized actions. So you pick a distribution and use that distribution to choose an action at time t. And so you put all these together, you get the policy profile, U. And so little u denotes a typical member of U, and each has components for each agent. Right? So once you have this, what are the objective? So the objective is going to be this infinite horizon discounted objective cost. So based on the policy that you have chosen and the transition kernel, you get the system evolves, and you get a measure on the process, and you take an average across that, but a discounted objective is what you're. We also have constraints, and the constraints, the constraint is also in the same form. It's a long infinite horizon discounted constraint cost. Right? So you average it again with the same measure, but now you throw in the discounted, the constraint cost. Now it'll turn out that this is where I specified these are what I would be calling as, I mean, they're not deterministic policies, but they are not randomized in a way. I'll tell you why. So what we'll have to do actually is look at mixtures of these policies. And this mixture, I'm going to call this set to be M1U. This will be a set of all probability measures on this set of policy profiles. This may not be very clear at this moment, but I need to give you a suitable topology, which I'll specify later on. So if mu denotes a member, typical member of this, then what it's saying is I'm going to choose an element u with probability given by mu of u, if you want to think of it that way. So essentially, I can use that to average these costs that are described above for every little u, and that gives me long-term all these costs and both the constraint, objective and constraint costs for a policy that randomizes over these policies there. So we will have to work with this M1U, and I will comment on that a little bit later on at the end. So having said this, what is the optimization problem that we have? So I want to minimize C hat of mu, which is the cost for these mixed policies that I'm presenting. So I can only choose mu from one of those mixed policies. But I want to respect the fact that the constraint cost is always less than the circular. Right. So faced with an optimization problem like this and knowing constraint Markov decision processes, well, you say, why don't you just take a Lagrangian relaxation, right? So I'm going to assume that C underbar is the optimal value, and if it is not, there's no feasible mixture, then it's set to infinity, but let's assume for now that it's feasible. So what we will do is construct the Lagrangian. And what we do in some sense is we only relax the constraints, have a Lagrange multiplier. Here it's going to be k-dimensional. So it's something that is non-negative and lives in RK. So it will be out. And we construct the Lagrangian function. And then we hope we can just optimize the Lagrangian function and somehow we have a good Lagrange multiplier, everything should work out. And the question you should ask is, well, that we know it works for the Markov decision, constraint Markov decision processes. Does it work in this generality? Can we make it function for this multi-agent setup? And that's essentially the main result of ours, that yes, you can make it work. But before I get there, I want to sort of give you a little bit of a flavor of why this is not straightforward. So it'll turn out that the way we are formulating, I have to use all the history and define my policy profiles on that. I cannot use the method of using occupation measures. That works for the single agent controller that was developed in Altman and actually the Borker and Altman. Borker pioneered the convex analytical approach, and sort of Altman sort of used that in a way for this constraint problems. So for us, we still don't have an occupational measure, so it doesn't simplify. The problem is still I have to handle this complex policy class and work with that. The second approach we could have done is, I mentioned the common information approach. Perhaps I could have taken that approach. It turns out that that is not that easy. It needs a lot of technical innovations, which I don't know how to do right now, but maybe it's possible. And the reason for that is because I'm working with, I have to look at randomized, as in the actions are taken randomized in a behavioral policy sense. This leads to an uncountable state space in the equivalent belief-based constraint Markov decision process that if you follow the common information approach. And that, I think, sits outside some of the current known methods to solve such measure valued processes. And so as far as I know, in the context of MDPs and POMDPs, we can only work within countable state spaces. So there's some technical challenges for which we didn't go that way. There are a few, yeah, go ahead. Yeah.
Okay, you're stating key assumptions. I was going to ask about some assumptions. I'll wait after this slide. Sure.
So there are a few key assumptions. The assumption, I mean, the transition kernel, everything is sort of general. There are a few assumptions for the results. So first assumption is that my objective cost is going to be bounded from below. I can have infinities, but it's going to be bounded below. So think of it as being non-negative. The second assumption is going to be the constraint costs are bounded from above and below. We would need this, and I'll tell you why that makes sense. The third assumption, we don't always use it, but this is critical. Essentially, we need some sort of constraint qualification. We're going to use Slater's condition. So there exists a mixture policy and a constant such that this mixture policy is strictly feasible, right? It's inside the feasible region. So yes, Daniel, you had some questions, yeah.
So in terms of information that's available,
Yes.
it's sort of abstracted away a little bit, at least for as far as I can see. But as I think about each individual agent, do they do jointly agree on a policy, right? Ex ante.
So that's what we're going to design, essentially. The policy will be designed, yes.
But it's one policy for everybody. And do they all, like, for example, know how many other agents there are, and like
yes,
that everybody else will adhere to that same policy and so forth?
Yes, yeah.
Okay.
You know the number of agents and the reason you will adhere to that policy is because you're not in a game, you're in a team.
Okay.
Yeah.
Okay.
So based on this, this is the first result. It's a strong duality result saying that, well, under assumptions 1 and 2, essentially on those costs, I can essentially interchange my maximization over Lagrange multiplier and the minimization over the policy. And this meets the objective that I'm interested in. Moreover, there also exists an optimal policy which solves the problem. Okay, so this is the first sort of sanity, big result in some ways, saying you're fine. We still don't have a Lagrange multiplier, and that's where we need the second result. If you add to the assumptions, you add the Slater's condition assumption, we get a saddle point. Essentially, there exists an optimal Lagrange multiplier lambda star as well. And furthermore, complementary slackness holds as well for the pair lambda star mu star. So I will just highlight the proof in a very quickly. So we need to develop a sort of a suitable minimax theorem to prove this. And I tried the pointer, but it's a little bit tricky. The minimax theorem says I have a pair of spaces, X and Y. They have to be convex topological spaces where X also needs to be compact. Now it'll turn out that X will be the policy space M1U, and Y will be the space of Lagrange multipliers. And this function F will be my Lagrangian. And so essentially it goes from X cross Y to R to infinity. I need a few properties. Fixing the Y component, I get it to be convex and lower semi-continuous in the first component. Fixing the first component X, then I get a concave function in Y. And the last part is where our innovation is essentially if for any xy you hit infinity, then if I change the y to y prime, I should get infinity for all y and y. Once you have these conditions, then the minimax theorem holds, and X star essentially here would be my optimal policy, and then it says I can do the strong duality is what. Right. So the second sort of idea or whatnot that is needed here is what is the topological space I'm going to be working with. So it turns out that U is in one-to-one correspondence with the following space. So this is a rather big object, and that's why I said this is a complex problem. So I first run over all possible values of time, and then I look at all possible histories for all agents, including the common history. So this is observations and actions for every given time. And then I multiply over all the agents, all possible actions they could have taken. Essentially, it's a randomized action. So it's a element of the set of probability measures on the action space for agent. Okay. So by our assumptions, this M1A is a compact metric space, right? Under the topology of weak convergence. And this infinite product is a countable product. Again, the assumptions that we had on the space. So this is compact by Tikhonov's theorem and metrizable as well. So I see that Sardar is in the audience. I should mention that this is also known as the WS topology, and I think he likes to call it the Borker topology. So it is living in something that is known in this area. And once we have that, the analysis step essentially says, okay, my M1U has all the properties I need in terms of compactness and convexity. And thereafter, I essentially have to satisfy, the Lagrangian has to satisfy all the constraints. So it is convex in mu, it's concave in lambda. What is trickier to show is lower semi-continuity. And the last example is essentially set up for the cost being under lower bounded. But the reason I need the constraints to have upper and lower bounds is so I don't subtract infinities and create trouble. Anyway, so let me just summarize these results because I want to transition to the next one. So this was sort of a general result for multi-agent constraint POMDPs in an infinite horizon discounted setting, showed strong duality and existence of saddle point. Now these results hold over this policy profile mixture space M1U, which is actually a joint mixing of policies across agents. And this is critical, right? And the way it's stated right now, the mixing is carried out at time 0 before interacting with the environment. And this mixing is needed to ensure tightness of joint constraints. Okay. Just like in the constraint POMDP, you need mixing to ensure joint tightness of constraints. Here, because we have joint constraints, we need to do joint mixing. It turns out that in this problem, I can actually take an alternate viewpoint. Once I have this result, I can take the common information viewpoint and also apply Kuhn's theorem. And thereafter show that this initial mixing is, you can either do that or construct a behavioral policy with just joint mixing at each time. And that could be more flexible and use, which is what I'll indicate sort of in the example that I have. Nevertheless, we have a complex optimization problem. No occupancy measures characterization exists as of now. We believe there may be some way if you make some assumptions, not at the scale level that we have right now. So the few things you should ask is, okay, you have a nice result, but where is it useful? So I will show you a particular use of it, and then we have a different use of it, which I cannot, since it's to talk about that as a different talk altogether, because of the details needed there. But I will sort of mention it towards the end. So the problem that where it's easy to see this is this wireless downlink video streaming problem. So let me sort of cast this problem and tell you. So I'm looking at a single base station, and it's a cellular downlink. There are n edge devices or mobiles trying to watch a video. Each could be watching a different video. And they are going over its wireless channel, which has errors and erasures, right? There is a transmission energy constraint at the base station. So essentially you cannot be simultaneously transmitting at high data rate to all agents simultaneously. So you have to pick and choose a subset, and that's where the constraint is going to come. The edge devices play video packets, and then they will be sending application level feedback to the base station so that these things control can be taken. Now the interesting thing is in a real system, and this is when I was at Motorola, this was something that we actually worked with. This application feedback is available at the base station with some delay. Delay could be because of errors or information processing, but nevertheless, there is a feedback delay. And so there are now essentially n+1 agents here. So each edge device is deciding whether to play out or not play out, at what rate to play out. And the base station is deciding whom to transmit to and at what rate. So this can be cast as a team problem with a common goal of providing high quality video streaming experience to all end users. And this is what is typically done in the wireless, in the cellular infrastructure problem. So what is done in with your service provider, for example. So this is a sequential decision-making model. Interestingly, the literature has only focused on MDPs, which is essentially looking at full and instantaneous information sharing, whereas this problem is a multi-agent problem with information asymmetry. Again, this is because of delayed feedback, and a lot of that has not been addressed. And our methods allow us to study this. So with constraints, the constraint that I mentioned, the energy constraint, we'll use the general duality result to study this problem. we'll show that there's a nice scalable solution that can be, which is not apparent in the beginning, will come up. And so essentially the goal here is to sort of, you're working as a team, expressed again as an infinite horizon expected discounted cost minimization problem. And then we want to identify structural results and thereafter use that to develop a learning solution, right? So let me speed through this a little bit. So I have n edge devices and one base station. I'm going to assume that there is only a state at each edge device. The base station has no state, as in it always has packets to send. That's a simplification, but that works for us for now. And the state at the edge device, we have two components. One is sort of the buffer occupancy, how many packets are there, and then maybe a quality of service or experience metric as well. And we're going to assume that the state is something that is finite value, even though we could think of countable space. Countably infinite makes the solution hard, but finite, at least we can explore how to solve it. So they have each edge device as a playout action, which is going to be denoted by VT. And this is in a finite valued. And you collect all these actions together, or you connect all the state together, it's XT. So the system state in that general result here would be the big vector XT. And the actions of the edge devices would be the VT. Note that each agent is only getting a partial view of the entire state. They don't get to see the whole state. The transmission actions of the base station are, again, deciding whom to transmit. So we assume that there's a finite choice. And I'm going to collect it all together in terms of this vector. Right, so I mentioned feedback from the client. So each client communicates its state and action to the base station. Even the action is not visible immediately because this is something that happens at a mobile. But both of these are communicated to the base station. It reaches the base station with a fixed deterministic delay for this problem. We can work with different versions of it, but for now, let's think of it as fixed delay. So what you should realize is the feedback is sent only to the base station. So the edge device, feedback of edge device N is known only to it and the base station, and not to the rest of the edge devices. So going back to the other general model that I said, there is actually no common information between the agents. There is private information. There's some parts where some agents know about other agents, but essentially there is no common information. So even developing a structural solution for this problem would be unknown, but what I'm going to say is our results allow us to transition to that. Okay, just quickly going through the system model. So the edge devices have their observations of the past state. I mean, the state evolution, what part they see, their past actions. They determine the past actions of the base station. They determine their playout actions. The base station gets a feedback, then it chooses the transmission action. But this doesn't have to be the layout, but this is one layout that we used for. For now, I'll keep the transition law as general. So the state evolves based on the actions taken by the BTS and the collective actions taken by the agents. And there's some initial distribution, which I'm going to assume is going to be a point mass on some X1. So we just go through the same exercise as before. Essentially, I'm not going to repeat all of this, but the thing I want to point out is here we have a single scalar constraint for the energy. This is based on the vector of actions taken. And here you have a cost for the, this is a cost that is quality of experience cost at the edge devices. Okay. Again, we have to look at the joint mixtures. Again, we'll go through, this sits within that problem. It's actually a simpler version of the general problem that I specified. So yes, you can define the Lagrangian. And it turns out in this case, the Lagrangian relaxant is extremely useful. It actually, under certain cases, makes the immediate cost separable. Right? And why is that important? So what we can use that and under certain assumptions, develop a scalable multi-agent control policy. I just want to highlight there is no common information. So we're still working with a complex setup. But there is, in some sense, some sort of, in some ways, you could call it nested information, as in, if I just look at the information the base station has about a particular edge device, and I just isolate that, that's given by this vector here, that is also known by the edge device, right? So there is some nestedness on that. And we are going to exploit that separation quite a bit. So if we make two assumptions, one is what I call the factorized transition law, as in knowing the base station and the edge device action, the edge device state, which is the only one that has a state, evolves independently. So I can separate for each, I have a transition law for each edge device, which just depends on the action the base station took corresponding to that edge device and the action that the edge device took. And that gives me how the state evolves, right? And I also have my costs being, immediate costs being separable. That is, if I look at the cost that I have as the objective cost, I can write it as a sum of the costs that depend exactly on the state of the edge device and the action taken by the edge device. I could also include the action of the base station here. And the energy cost is just dependent here on the actions taken by the base station corresponding to that. I added as a sum of those energy costs for each action. Right? If I have these two, so this is, and furthermore, when I add the Lagrangian relaxation, essentially it's going to add all of these things in a separable manner. And that will essentially help us mention the third result here. What I can do here is structurally decompose the problem into n independent unconstrained transmitter-receiver problems. So I'm fixing the Lagrange multiplier here. And I'm saying what is the structure of the policy that I get. The way I want to understand that is, suppose I fix the policies of all the edge devices to be G, so G1, G2, G3, Gn. Then every transmission policy of the base station, for every transmission policy, there exists a factorized transmission policy. Essentially, a policy that can be replicated as n. A way to think of it is to conceptually think of the base station being separated into n controllers, where base station 1 only looks at the information from edge device 1 for its action, choosing its actions. And similarly, base station 2 only looks at the information from edge device 2 or taking its actions. So this separation makes it essentially n independent. I mean, this is under the case of when I fix the Lagrange multiplier, n independent pairs of problems, right? So pairs of controllers. So this is a structural result, which can then be used to solve for the optimal policy, which is what I'm going to sort of show you right now. So I can essentially concentrate on a single transmitter-receiver problem and try to solve that. And here is the cost objective function. Here I have the Lagrange multiplier that I've fixed in. I have the energy cost corresponding to the action taken by the base station, and this is the objective cost for the original objective cost. So this becomes the objective cost for the single transmitter-receiver problem. And the interesting thing here is that the delayed feedback from the receiver is now common information to both agents. There was no common information earlier across all the agents, but when I look at just isolate this pair, I have common information. And this actually sits in what's called the delayed sharing information structure. And this can be exploited. So then we can sort of rely on the common information approach to sort of solve this problem by instantiating a coordinator. Here, the coordinator turns out to be the BTS agent, because that's the agent has the same information as the common information. And from that coordinator's perspective, the unknown state is the entire future of the edge device. So essentially the state as well as the actions that the edge device has taken. And all you need to do, if you follow the common information, I have an information state now, the common information-based belief on this unknown state. All right, but this tells me how I should think about constructing these policies. This is strategy independent, but model dependent again. But the nice thing is it's strategy independent. And so we can then think about, can we actually leverage learning to try to solve for an optimal policy? Because it's still a very hard problem. You won't be able to, unless you have more structure, you cannot develop an optimal control. Okay. So that's what I'm going to sort of go on next, is sort of, this is actually summarizing a big work. And we have some extensions of that for the primal dual thing for the constraint problems, which uses the result that I mentioned before. But I'm going to just talk about it in a very high level, because I guess I have over 10 minutes to go, or 7 minutes to go or something, right? Anyway, So with the model unknown, essentially model here is the channel erasure probability. I don't know that. Using the channel common information approach is challenging because I cannot construct that belief state. The other issues here is also the private information of the agent, even though it's finite, it's a finite domain. So this is what we have. It's fixed time invariant domain. It's large. If D is large, if D is 10, I have, it's living in a very, so it's exponential in D. So it's a large state. So it's large in time invariant domain. The common information grows over time. And so I would want to compress that. But if I have to use the belief state, which is an information state in this problem, I need model knowledge. So this is usually a challenge that we have. So one way that we developed, and this is the work that I mentioned was with my student Sugao, which was we can develop an approximate information state. Essentially, what we say is you come up with a different compression, which is not as good as the information state, and you have some error criteria for that. And then you solve that based on that, solve a optimal control based on this representation that you have created. And then the solution that you obtain will not be too far off from as if you had the whole information you were solving. And the nice thing is the way these error criteria are set up, you can actually learn it in a data-driven manner. I will show you one experiment for that. And what this involves is actually compressions of both the private and common information in the team problem setting. And as I said, the results characterize formally what's the performance loss in terms of regret. Now, this method, I should mention, it sort of builds on work that was developed by Aditya Mahajan and co-authors, which was originally developed for partially observed Markov decision processes. Here, I should also mention work by Ali Kara and Serdar Yüksel, which also proposes an AIS for POMDPs, and that also is applicable in the context of multi-agent systems. The one thing that may be useful to mention here is where does this sit in with respect to things like function approximation? So you should think of this as very much similar to function approximation for large-scale MDPs. So what you're doing there is your state is very large. So I want to come up with a representation of the state which is smaller that I can work with. And that conceptually is actually creating a sort of a partially observed Markov decision process that you're trying to solve. And this view actually has been, and so if you can learn it from history, you will do better. Showing that this actually works out is a recent work by Aditya Mahajan and co-authors, which I'm sort of pointing to here. So in some sense, this sort of helps you formalize function approximation as well. But nevertheless, we are looking at function approximation type ideas for a complex problem, which is a multi-agent problem. That's where the approximate information state sits in. So I'll just quickly go through some numerical results to show that this actually works. So I'm going to have a stylized Lagrangian cost, which the base station has 3 actions. These are with decreasing power. So it's sending a single packet with a certain number of sub-packets in there. So the power goes from high, medium to low, and the probability of error goes from low, medium to high, as is to be expected. There is some cost based on the power. The numbers give you the cost. Each edge device has a playout buffer of size B. The parameters used for the simulations will be mentioned later on. They have 2 actions, play out or not, and there's a reward R for play out, and the cost is K times the number of stalls because we keep count of the number of stalls. I mean, the stalls are when there's the play out buffer hits 0. The Lagrange multiplier is fixed here. The table that we have just specifies the values of this. I'm going to assume that each episode is of length about 50 time steps. I mean, discounted cost problems are very similar to finite horizon problems. The discount factor is 0.95. As I said, the state space for each edge device is buffer length and stall count. I have a maximum value of 30 there for both. So this is a large state, but nevertheless can be handled. The transmission success probability, so this is reversed from the error is 0.2.85. So this means that it's very the success probability very high, success probability error probability very low, 0.15 to error probability 100% on this space. And here are the parameters we do for the training. We're going to use about 30,000 gradient steps. I'm not showing you the architecture. There's actually a nice based on the approximate information state, we can construct like a underlying neural network architecture to try to learn it. Don't use very large systems, but like 128 parameters for LSTMs that are used underneath, and there we have some feed-forward networks that have about 64 parameters. So I said 30K iterations in training, we're going to have about 1K test episodes that we'll average. Right, so let me just show you the numerical results, and then I have one more slide to conclude. So you consider two alternatives. One is going to be this, all that I've described thus far, the common information approach with a controller at each base station at the edge device. This is the multi-agent AIS in the plots. The second one is what was just direct extension, what was done for the MDP setting in these problems. Essentially, it's a delay oblivious problem. It assumes that the feedback from the edge devices is the state of the edge device, and essentially I'm going to use that to determine my policy. And what we'll be studying is what is the impact of the delay. If delay equals 0, both have the same information, they should do the same thing. And as I mentioned, what my Lagrangian cost was as well. So the first question you can ask is, can you successfully train these this multi-agent based video streaming policies with partial observability? Can you actually make this all work? Turns out, yes, you can. So I'm going to contrast here is the single agent problem where blue one is delay 0, and as I increase the delay to 10, the performance dramatically drops because now I have very stale information. I'm using that to take actions. In the multi-agent case, I do the degradation is much lower because I am anticipating the fact that this is delayed, and I'm forming a proper belief on the state of the agent. And that helps me substantially improve over the single agent framework. So the other thing that you want to look at is, okay, this is fine in terms of the episode rewards, but can we say a little bit more? Can we look at the details a little bit in terms of stall counts and what is the policy in some sense? So if you just look at the episode rewards, you're actually doing better. We are doing substantially better. That's there in these charts that you can see. This is for different delays. Here, if I fix a delay to be, I think delay was fixed to be 10, there are fewer stalls for the multi-agent system than the AIS. Essentially, the buffer doesn't hit 0 that as frequently. The more interesting thing is if you look at what policy that results, this is when viewed from the edge device perspective. So the base station is sending a lot of packets in the single agent setting, even when there's a large playback buffer. Whereas in the multi-agent setup, the buffer is very tightly constrained around a small value, right? And this is one of the sort of benefits of going to a multi-agent setup. So hopefully I sort of described how taking these approaches will help you solve some of these multi-agent problems, at least team problems. And I believe that we are at a point where we can solve many more of these problems using the conceptual approaches as well as the computational tools that we have. And so this was an example of that. So I want to conclude by sort of saying, are extensions to dynamic games possible or not? Or where are we with respect to that? And in this case, I want to sort of highlight a joint work of mine and actually a PhD thesis of my student, Deng Tang. I mean, he's graduated, he's a postdoc right now. I had shown him in the beginning. And one of the messages that his thesis and this work shows is information state can be hard to characterize in general in dynamic games. And I feel that's something that's a challenge for research. So what his results show is that for some models, model and strategy independent information states exist. And so then you can develop equilibrium using strategies with just this compressed information. They exist as well. And for certain characterizations, you can also preserve all equilibrium payoff profiles. So you can say something very strong, but in general, the domain of these information states grows with time. So this is like the case that I had mentioned in the POMDP earlier. That's partly why I had this thing. You have model and strategy independent settings, but the domain is growing with time. What you would say is, hey, we did all these belief states. Would that work here? So yes, you can try to use the common information-based belief state as a candidate information state. And in many cases, in many examples, this belief state has a time invariant domain. So it seems promising. But the problem here is that this belief state is not only just model dependent, it's also strategy dependent. different from the team problem, this is also strategy dependent in general. And this is a big stumbling block because what we can show in his thesis, and we are writing a paper on this, is equilibrium may not exist in general. There are lots of examples in that upcoming paper where equilibria don't exist. And in fact, even if equilibria exist with these things, sequential decomposition ideas may not carry through. And the examples are quite challenging, I think, to the research community. I think it throws up a lot of questions. And it's of the kind, the examples are of the kind, you give me a delay, and I'll have to go back, pass that delay, pick up something, just pay off irrelevant, and use that to sustain any equilibrium in that problem that I want. So they challenge our notions of how we decide to what information to keep and what not to keep. And a better understanding of this is something that needs to be developed to make progress in this space. This is what my takeaway is. Anyway, with that, I conclude and thank you for listening.
Thank you, Vijay. Do we have questions from the audience? Doesn't seem like that. So in that case, let me remind everybody of the upcoming talks that we have in the SNAPP series with Yuxin Chen on April 22nd, Pascal Moyal on May 6th, and Theodoros Likouris on May 20th. And thank Vijay once again for his talk today.
Thank you, everyone. And as I was just going to add one thing, that I guess I did make it on time so that anyone who wants to go chase the eclipse can go chase it in North America at least. So it's one of my first things to have to compete against an eclipse, but I guess I do give you enough time to get it, make it if you can.
I hope you'll catch a glimpse as well.
Thank you. All right.
All right. Take care.
Take care.